So as a supplement to today's online class, I'd like to talk a little bit more about distribution system fundamentals. And so I'm going to kind of cover a couple different things. I'm going to talk a little bit about the distribution circuit components, and then I want to then get into a little bit about what smart grid is and how this is going to tie in with distributed energy resources or DER. So this is the diagram that I showed earlier today in the first lecture, where basically I was talking about like generation, transmission, and distribution. And what I'm going to do is I'm going to talk more about what are the specific elements that we can actually see in a distribution circuit. And these are typically elements you can a lot of times see like at the street level if you're walking around a given area. And so first at the top of each circuit, we have a distribution substation. And what the distribution substation does is it's going to go ahead and convert the transmission level voltage down to distribution. And so this is converting the voltage down to this, 4 to 40 kV level that I talked about before. And there's a number of different components in a substation, which I'm going to get into in just a little bit. A lot of times there's focus on substations because there's so many components in here and it's such a critical part of our system. And so within here, we're going to have the voltage control. This is where we're going to regulate the transmission voltage for the distribution feeders. We have our circuit breakers in here, so we have the protection elements. And then we can also have circuit switching. And so we'll see later on when we talk about substations in more detail that we're going to have redundancy. And so if we have to take a section of the circuit out for an outage, that we can switch our feeders around and still maintain continuity of service. So within the substation, again, what you're going to have is you're going to have an incoming source. I'm showing a single source in this case, but a lot of times it's actually a source from the left and a source from the right for reliability purposes. When we're talking about doing the conversion, we could have one transformer. A lot of times we have two transformers for redundancy's sake. And then we're going to have our voltage regulation. In this case, I'm showing two line voltage regulators. Sometimes though, what utilities may do is they may put their voltage regulators on the top of each feeder. So this varies from utility to utility. And with each transformer, then you'll have a bus. This is where you can connect up feeders. And you'll have outgoing feeders, which will go out to the different load groups. And so in this case, I'm showing a total of 4 feeders. Note what you can do is you have a tie switch between the two buses. And so let's suppose this transformer on the left has to be taken out for service. What we can do is we can, it's not shown in this case, but there's going to be a disconnection switch here. And what we can do is then we can actually then transfer load from one bus over to the other, right? And so anyway, this is what we're going to have for this particular substation in this case right here. So then what we're going to see later on is, there's different types of substation designs as far as whether you have like one substation or multiple substations. And then we'll have various sort of options as far as transferring load back and forth, which we'll show in the future. So the key component in one of these substations is going to be the substation transformer, obviously, right? And these are going to be 3-phase devices. They're going to be in the MVA level, 5, 10, 15, 25 MVA. What you'll also see with these devices is a need to cool them in order to dissipate the heat that's generated due to losses. And so you'll see fans mounted to these devices with cooling fins. There's circulating oil through here, and then you'll use the fans to help cool out the oil. This is why on transformers, you typically see multiple ratings. There's a rating with no cooling fans, and then you usually have this broken into 2 or 3 banks of fans. And as you turn the fans on, then you increase the rating of this transformer. Some of these transformers will have built-in mechanisms for actually controlling the voltage. And so that's just something else to kind of keep in mind in this case, is, you know, where the voltage regulation is actually going to be at. And in many cases, we have these built into the unit, or they could be separate unit. It varies from utility to utility. So protecting each feeder coming out of the substation, you have a feeder circuit breaker. This is typically where we kind of start our analysis, is up at the top of the feeder for the circuit breaker. There's going to be a relay associated with this. What the relay is going to do, it's going to monitor the voltage and current. And if there's a fault detected, then it'll actuate this circuit breaker open. What's also associated with this relay is also top of feeder measurements. And so this is going to be useful information for operating the circuit. So then we get outside the fence. All these components I've talked about, as far as a transformer and the station regulation for voltage and the breakers, these are all within the substation fence. Then you get outside the feeder, kind of like at the street level. And what you're going to have is usually it's going to be a overhead as far as your main part of the feeder. Sometimes I'll refer to this as the backbone. And then when you connect to loads, what you're going to do is you're going to run taps off this main feeder. And these are oftentimes either called laterals or taps. A lot of times it's a single phase, but it could be two phase or it could be three phase. And these taps are typically fused. And so they could be overhead, or you can actually go to underground. And so you can actually have a tap come off and feed transformers through cables. Other components you're going to see components like recloser. This is actually for providing protection as well. And what this does is it bisects the circuit, converts the circuit into two different parts. And then you'll also see many times a tie switch, which connects to an alternate circuit. And so what we can do in this case is we can actually transfer load from the circuit on the left to the circuit on the right. And this kind of helps us out for reliability purposes. I've also got shown in this diagram a switch capacitor bank. This is used for power factor correction, helping to control voltage, as well as a voltage line regulator. And a lot of times I'll call these devices outside the fence line voltage regulators, just to be clear that these are mounted up on poles as opposed to the devices we have in a substation. And then you have your connections then to the customers through these distribution transformers, which steps the voltage down from a medium voltage to a low voltage. So anyway, this is kind of more of a schematic type of a diagram, which we refer to as a one-line type of a diagram. But as I mentioned in the online class, you know, you have a geographic view as well, because these distribution circuits are typically going to follow streets, you know, main streets usually. And then when you get closer to the loads, this could follow the street, or they can go through alleys, whatever. But most of the times these are going to follow the streets. And this is going to be usually overhead coming out of the substation. And then when you get closer to the residential areas, you might see more underground cabling being used. So for our overhead, for our primary distribution, what you're going to see is a lot of three-phase overhead. You might actually see single phase and two-phase as well. And then when it comes to connecting to transformers, then you may see this transformer mounted up on top of the pole. And then this secondary is what goes to the customers. In more urban areas where you have a lot of customers, sometimes we'll even run these secondary wires up on the poles as well. And so you see this 120/240 volt service that you can connect service drops to. And this would be the case if you had like many customers hooked up to one of these distribution transformers. Utilities also need to share their pole space with other utilities like phone and cable, like cable TV service or internet service. And so you see below, a lot of times you're going to have the phone cables or the other cable services. They're conductors are going to be mounted up here as well. And so this would be like an example of three-phase service. And then when you want to make connections that are protected, then you make use of what are referred to as these fuse cutouts. And so what these fuse cutouts are going to be containing, they're going to be containing these fuse links. And if this would blow, then a lineman could actually use a stick and actually remove this fuse link right here and actually replace it. And then they could actually even use this as a switch a little bit. They can actually open these manually as well. So when you see these up on the pole, basically, you know, what you can do is you can use this as a way of protecting like downstream service. This could be used to protect against downstream faults. You'll see this on single phase, that here you have a three-phase service and you have a tap here, and this is used to provide like single phase load to this lateral in this case. And so here's an example of what a tap looks like. And the reason it's called a tap is you can see there's a physical connection that's actually made. So when you're walking around, you know, just take a look at this overhead. I mean, you could actually see a lot of this on your own. Now for underground, where we use underground is in some of the newer areas where we have residential, commercial, and we don't want to use overhead because maybe that's unsightly or kind of cumbersome. And so we usually would have underground for that. And what you typically would do is you would run this in a loop type of configuration. Now this is still operated radial with an open tie switch, but what you're doing in this case is you're actually providing the ability of having redundancy. And so for example, if I were going to lose this cable, what I can do is I can unplug the cable here, I can unplug the cable here, and then I could feed this customer through this tie switch by actually closing it. And so a lot of times underground is actually set up in a loop. There's actually two connection points for underground. So the transformer we would use for this would be what's sometimes referred to as a pad mount distribution transformer, where there is the three-phase connections maybe coming from the primary, then you have the three-phase connection going to the next transformer location. And these are located typically on pad mount concrete pads. For line capacitors, the line capacitors that we're going to use are basically in the format of like a can. We'll talk later on about how we would make these devices, but you would mount these up on the pole, and if you wanted to have these be switchable, then you would have typically nowadays, which would be vacuum switches. These used to be called oil. These used to be oil switches, and associated with the control, you can open and close these capacitors, where the sizes would range, you know, maybe between 300 and 2400 kVAR for each location. For line regulators outside of the substation, we have these special units. These are what are called auto transformers, and we'll talk later on about what an auto transformer is. A lot of times if you have three-phase, these are rather heavy, so they'll come up with special mounts where these will be located in a platform on the field. And you'll see these outside as well. So there's a feedback controller on here. This is actually a controller on the unit. And what that controller does is it makes sure that the output voltage is regulated to a certain point, to a certain control set point. We'll have overhead manual switches. There'll be a lot of these switches out in the field where you can actually open and close them. This is important where if I have a fault on a section, I want to isolate it. And so the more of these manual type switches I have out there, the more flexibility I have in removing sections of faulted feeder from the circuit. And then these can also be motor operated. And the reason you want these motor operated, if you want to automate the restoration process. And so this could be controllable through a SCADA system where you have a motor control, it has communications on it, and the operator could actually talk to the switch and actually operate it remotely. Usually these types of switches can break a load current, but they wouldn't be set up to break a fault current. You need a breaker for that. And so these don't have the same ratings as like a recloser or a circuit breaker. And then you'll have underground switches, which are actually set up to switch around sections of underground cable circuit, which can contain fusing as well. And there could be automation associated with these sort of underground type of switches. Now, once you get outside the substation, if you want to have protection and you want to be able to clear a fault current, then what you're going to need is you're going to need what's called a recloser. It's called a recloser because these devices are actually set up where if they detect a fault, they'll clear the fault, but then they might close in a short time later because many of these faults are going to be temporary in nature. These reclosers usually consist of 3 independent poles, and these poles could actually be controlled separately. So you could actually do independent phase control in the field. You typically won't do this in a substation because of 3-phase load, but when you're closer to the residential customers, you can actually do your operations on a single phase basis. And so these are going to be magnetically controlled switches where you have a mechanism in this cabinet which actually controls each individual pole. There's also older types of devices out there where instead of using vacuum bottle technology, you would actually just use an older oil circuit breaker type of technology. And these are what are referred to as hydraulic line reclosers. These are not electronic, that's all kind of mechanical based. And so this is used a lot of times for single phase still. You might still see 3-phase out there. There's not as flexible as electronic device with the electronic controller on it, but they're highly reliable. And if you want to have something located remotely, this might be a good option for single phase or 2-phase. And then when we get closer to the customer, then we have to step the voltage down using a customer distribution transformer. And these could be mounted up on the pole, or these could be located near the ground, but a lot of times these are mounted up on poles. And so this is kind of like the standard transformer that you've probably seen before in other classes you might have taken on power systems. Note that you have to mostly provide protection with these devices. You could have self-protecting devices, but a lot of times you have to add like a fuse, or you have to add a surge arrestor to this when you mount these out into the field. We get to the customer also, we have to monitor the energy consumed. And so each customer is going to have a meter box. This would be something typically that the customer would own. And then when utility puts the meter into this box, and that makes the contacts for customer service. And so as soon as the meter is installed, then the utility can start measuring the energy consumed. This is actually showing some of the newer meters where these devices could have like 2-way communications, we would call these smart meters then. And then when we get to the load, there's a lot of different types of loads out there, like heat pumps. This is for heating and cooling. These are kind of popular in the United States and the South. When you get into the northern regions, heat pumps aren't as efficient, so people would tend to have more like gas heat. Even around in the Carolinas, we see a lot of gas heat being used. Other significant loads would be water heaters, washers and dryers, refrigerators, and then the smaller loads would be like lighting, TV, and appliances like that. Another sort of large load is going to be cooking. So if you have a range where you have something you're heating up or something in the oven for that short time period, there's a lot of consumption associated with that. And then a new type of load would be electric vehicles, where you're charging up these vehicles. So when we talk about applications, a lot of times people are going to talk about smart grid. And this is just a definition from Wikipedia, where basically smart grid's kind of the intersection between conventional power engineering and information and communications technology, or IT and communications. And so basically, if I take my conventional distribution, if I enable it with communications and have ways of processing that information, then I have a whole new range of applications I can develop, which is what we refer to as smart grid applications. This is also associated with having distributed energy resources, because then we would use our grid communications infrastructure to talk to these devices out into the field. Another term you're going to see a lot is grid modernization. A lot of utilities have kind of been shifting from talking about smart grid to grid modernization, because we realize there's a lot of conventional grid technology out there, a lot of assets out there that need refreshing as well. And so instead of just focusing on the communications and putting out relays and stuff like that, we really have to kind of think more holistically about, well, what do we really want to be doing in terms of conductor sizes, and whether they want to use more underground, or we want to start replacing circuit breakers and transformers and things like that. So the grid communications infrastructure can get pretty involved. And what this is showing is we have all these devices in the field. We've got like meters, we've got reclosers, we have capacitors, measurements we're taking. And all this information can be obtained through like a radio infrastructure or using cellular. And if we have a network, if we have a wide area network, what we can do is we can bring all this information back. So in this case, this is actually showing like a head-end system, which is used for processing all this information. And this eventually feeds via utility network to all these various applications, say like SCADA or volt bar control or outage management. This communications infrastructure is what we cover in the course that's taught in the fall, ECE 586. And so we're not going to get into the details here on communications, but just realize that if we can get all this information back, then we can actually enable some more sophisticated applications for managing our grids. So one application area is going to be volt bar control. As far as a financial benefit, this is actually very important, because this actually can save utilities a lot of money. And so we'll get into this later on. Primarily this involves control of capacitor banks and voltage line regulators. We need to have measurements for this. Sometimes we get measurements from the meters. We also have to get information out of the substations, which can come back through some different paths. Usually, this is more through a higher speed network that the utility would have. But when we combine all this together, then we can have intelligence at the enterprise level that could use for doing things like controlling voltage and reducing line losses and things like that. So we'll talk about this more toward the end of the semester. Something else that we see enabled is higher levels of penetration of distributed energy resources through this technology. And so if we're talking about residential PV, you'll have like panels up on the roof, and then there'll be an inverter that converts the power from DC to AC. A lot of times you connect either through the customer meter or a separate meter, and this ties through the customer meter box into the utility system then. And so you could have like residential systems, which could be like between 5 and 10 kilowatts in nature, that are single phase. Or if you're talking about what we call utility scale, you could actually have these larger 1 to 20 megawatt systems hooked up. Usually these are closer to the substation, where you have many, many panels interconnected together with multiple inverters that actually would feed back into the medium voltage grid. And of course, the reason a lot of developers want to do it this way is they don't have to pay the cost of a new substation if they can go through the existing distribution substations. So if we start then adding these different types of distributed energy resources to our grid, either megawatt scale or residential customer scale, then there's all sorts of things we're going to have to be concerned about now, because these distribution systems were not originally designed for this distributed generation. If we have a system that was built in the 50s, 60s, 70s, even the 80s, nobody really foresaw that we're going to be interconnecting distributed generation and want to backfeed this back into the transmission grid. And the issue we run into, especially with PV, is a lot of these resources are dependent on the irradiance of the sun. And so if we have clouds, then what this does is this impacts the irradiance and this impacts the power output. So the power output from each of these individual units modulates up and down, maybe between 100 and 30%. And so as the power modulates, it causes fluctuations in flow back and forth on this grid that cause rapid fluctuations in voltage. It can confuse our relaying, put some constraints on how we operate our protection, causes a number of different sort of problems. I mean, we could actually get to the point where we can overload this substation transformer in the opposite direction. And so this is kind of what we're starting to look at now for distribution, is how we can basically operate and design these circuits to facilitate higher levels of distributed generation. Okay, so anyway, that just gives you kind of an overview of the components out there, and also some of the things we're concerned about for smart grid. And as we go through this semester, then we'll be talking about this in more detail, and you'll see these same types of diagrams in the future, in future class lectures. But I just want to kind of go over what these various components are and the types of systems we can build. And again, you can see a lot of this stuff if you just kind of observe it. So, you know, the next time you're walking along, don't do it while you're driving, but when you're walking along, just kind of pay attention to what's up at these poles and the pieces of equipment up there, and start to, you know, relate this to what we're talking about in class. Obviously, you're not going to be able to walk into a substation because that's all our protected areas, but you certainly can see everything that's up at the pole level, at least, right? Okay, so anyway, that's all I really have to say about this. Thanks.